This is Dr. Frederick, just talking about what is a tabled value. And a tabled value is a couple of things. In the first place, when we started talking about z-scores, a tabled value was a place in this z-table that you're looking at. And one of the tricks was trying to correspond what we saw in the z-table with this calculator. If we look at something like this, then a z-value represents the distance from the mean, and here we have, our distribution goes up to z equals 1. This corresponds over here to a z equals 1.00. And we're looking at a value right here that says 0.8413. And that corresponds to this 0.8413 over here. And what it means is that 84.13% of the z-scores are at 1 or lower. And so the idea here is that a tabled value represents the probability of seeing something. And here the tabled value means that you're 84.13% likely in a normal distribution to see a z-score of 1 or lower. So the tabled value is always a probability of seeing something in this sort of setup. And that's what the z-table represents. Let's say it a little bit differently. Let's say that I want to find that part where there's a 5% chance or less of seeing something. And so I would go down here and put 0.05 in the shaded area and put it in here, and I see that the z-score is negative 1.65. And so I can find 1.65 here positive and see that it corresponds to 95%. Now, that's tricky for some students because they don't get that, but all you're trying to do is to flip it over in your head. If you went up to 1.65 positive z, 95% of the curve would be there and 5% would be out here. So there is a correspondence in table values between the values of the test statistic and the probability. And what happens after the z-tables is that many times the probabilities on the outside of the table and the values of the statistic are on the inside. So let's take a look at that. So before we do that, let's just take this sort of attitude. Let's imagine that this normal distribution here, this normal curve, is a distribution of samples in which we compared one sample to the other. And what was true about the populations that they were drawn from was that the means of the populations were the same. And so what we expect is that most of the time the modal value of the mean differences in our samples, let's take a sample from population A and a sample from population B, most of the time there will be no difference between those sample means. And sometimes we'll draw samples even though the population means are the same. The sample differences will be way down here, a very small part of the time, and way up here, a very small part of the time. And this distribution represents the frequency of differences in sample means in terms of the magnitude. Most of the time there's no difference in the sample means. And so we could say this is a distribution of sample means under the null hypothesis when there is no difference between populations. And that's exactly what all other test statistics are. It is a distribution of the test value when the null hypothesis is true. So let's take a look at this. Here is a table that shows the distribution of correlation values when the null hypothesis is true. Here we see some R values. The R values are in the table. And this sort of distribution says where is the R value? What are the extreme R values when the null hypothesis is true and two populations are completely uncorrelated? We'll take two samples, one from each population, and correlate them. And sometimes they will be correlated even though the populations are not. And depending on the sample size we take here, very small samples to very large samples, the larger the sample you take, the more the samples look like the population. So when there is no correlation in the populations, you see very extreme values of the correlation are something like 0.05 to 0.1. You're just not going to get that much correlation in the samples. But when your samples are very small, the extreme values can be rather large. So how do you read this? This says, if I come from the left and I look at the I'm sorry, this is two-tailed right here. If I just show you the distribution of correlation coefficients when the populations are not correlated, these are the extreme values. 5% of the time, I'll see correlations of magnitude 0.95. And so you have to have a really, really strong correlation to reject the null hypothesis, and that's why you just increase your sample size to something reasonable. Let's look like a 25. Here, even when the sample sizes are 25 and the null hypothesis is true, you can get correlation coefficients as high as 0.505. And so if you're trying to establish whether two populations are correlated, it takes a very high correlation in the samples to reject the null hypothesis, and you reject the null hypothesis when your observed value is greater than this critical value. And the critical value is just an extreme value of the test statistic when the null hypothesis is true. And so that's the answer to the question. The tabled values are always the values at some extreme level when the null hypothesis is true. When our observed statistic is greater than the extreme value, we reject the null hypothesis because we say, no, it's just very unlikely to see that if the null hypothesis were true. And the tables give us a benchmark for making that decision.